Okay, hi everyone. This is number 18 from tonight, and I just started working on it here. It's this milk carton width by length by height. The volume has to equal 512. I'll come back to this in a second. And you're asked to minimize cost. And what I did here was I just set up my cost function. It's 1 cent per square unit on the four sides. So I have two of these panels, W times H, right? Two of these panels, right? And those two areas will cost 1 cent per square meter. And then I have the length and the width, the top and the bottom. The top and the bottom cost 2 cents per square unit. And so notice that my cost will be in cents because I don't feel like dealing with decimals here. Okay, so then I took my cost function, which I noticed that C is a function of 3 variables. Luckily, I can go here and use this equation and solve for 1 variable, which then allows me to substitute in L for L, which brings me to here. Okay, and then all I did was clean. All right, and then because of the constraints, what I said here was I know my domain restriction is W can exist from 0 to some upper limit. Similarly, H can exist from 0 to some upper limit. The important thing to recognize here is that notice that these are soft parentheses because you know that 0 is not a viable alternative because you would have no box. I made a note down here, this is the question of what this upper limit is. I don't really care what it is, frankly, because I know that whatever the upper limit is, it's going to be open, all right? Because if you scroll back up, right, the greatest the width could be, right, if the W was the absolute greatest value that the width of this cardboard carton could be, then this is what Connor was talking about. You'd essentially have no box, right? Because the volume here, essentially, if we took that volume and it's kind of a weird idea, but basically stretch this out over a one-dimensional plane, you wouldn't have a box. Same thing goes for the height, right? So I guess the point that matters here is I don't really care about what this upper limit is. The point is that I'm looking at a domain whose boundaries I don't have to consider as locations for any critical points, okay? Because this is an open interval. So I actually am very happy when you're asked to optimize something over a non-closed domain. So this is a bounded domain, boys and girls, but it's not a closed domain, all right? Closed would be inclusive endpoints. So the point is, I don't really care what this upper limit is because I don't have to deal with the boundaries anyway, all right? So now here I took my cost function, I took the two partial derivatives, dc by dh and dc by dw, all right? And Oliver, this is what we were talking about in class today. And Oliver, actually, this makes me wonder something. I don't know if you ever got the notes that you missed from when you were absent on Friday, so that could have been why you were feeling like you were thrown to the wind in class. So I found these two partial derivatives, and what I need to do is set them both equal to 0 because the critical point or critical points will be points that make both of these partial derivatives equal to 0. Now, you'll notice something. Unfortunately, here, this equation and this equation, they are both equations with 2 variables. I don't have a situation where I say, I get a situation where I have okay, W equals 7 here. I don't have that. So the way to find the values of H and W that make both of these equations true, I'm setting up a system. Okay, and so now here's the green system. The bottom equation, look to the right. I just solved that for H. I'm using substitution here. I then subbed H in for H of the top equation. And I'm here, and I'm here, right? And at the end of the day, what I get is this. So W could equal 0, or W could equal negative 1/2, positive 1/2. And already, this I know I can completely eliminate. W can't be 0. So the width, it looks like, could be 1/2 of a centimeter. Is that right? A half centimeter? Okay, and then the question is, when W equals 1/2, what does H equal? So when W equals 1/2, what does H equal? H will equal 512 all over 1/2 squared. This will equal, what, 2048? Okay. All right, just give me a second to check my algebra here. I went through very quickly. Hang on a second. Here's my algebra mistake. It was silly. Look at the blue. H equals 512 over W squared, right? So when you plug that into this equation, the top equation, you get 2048 all over H squared. I have to square it, okay? So when you take care of that, the equation you get is down here, correct? And then what you get here is the following, right? Okay, so W 2 minus 1/128th W cubed, all this equals 0. You know that W equals 0 is a solution we're going to disregard. And then here we're going to get 2 minus 1/128th W cubed could equal 0, right? So then 2 times 128 is that 556 equals W cubed. So W equals the cube root of, 120 that's 256. Oh my gosh. Cube root of 256. Okay, so there is your width. And when W equals the cube root of 256, H will equal some number. I'll find that, hang on. It equals, okay, so now what we have here is I just found W, I just found H, so here's H. These are in inches or centimeters. So this is the centimeters, this is the centimeters of the height, right? Okay, and then we found the critical point. There's only one that makes sense. We have to now show that that is where C is minimized, okay? Now, what's interesting here is I'm going to do this. I'm actually going to do this. I was kind of thinking about what, I think it was Eric and Max or Eric and Robbie. Anyway, about their question was, hang on one second, I gotta do something. Okay, I'm gonna make, because I can't scroll. You know what, I'm gonna do this, boys and girls, hang on. I have to make this really teeny weeny. I'm gonna go over here and take the second derivative of C with respect to H, and what I get is positive 2 times 2048 times H to the negative third. And then here is this one, the second derivative of C with respect to W is equal to 2 times 1024 times W to the negative third. Okay, then I'll expand it. I was thinking what they were saying the other day about, I showed you that second derivative test for relative extrema, and it's like, can there be kind of like a back way around it? I don't know. I mean, I struggle. I don't know. But I will say, whoops, I have to do one more. Oh dear. I was thinking about that, and I don't know if, I don't know. It makes me kind of wonder. I don't know. Okay, I'll have to take this mixed. So this, the derivative with respect to W of this will equal 2. All right, let me expand it all the way back out. Okay, so now I have to show that this occurs at a minimum, right? When W equals this number and H equals this number, cost is minimized. So the first thing I did here is I looked at the second derivative. So I looked at d squared C by dh squared. And I want you to notice something, that for all values of H that are viable, in other words, for values of H that are non-negative or non-zero, I want you to make a note of the fact that this is always going to be positive. Similarly, d squared C by dw squared is also going to be positive, Okay, so what that tells you is the cost function is concave up in the h direction and concave up in the w direction, which reinforces the idea that I'm likely looking at a min here. Okay, like that. So in other words, all indications are good that this point is also a min, correct? Okay, now in case you're curious, I treated here h as the x variable, w as the y variable. You can do either. I'm also noticing that the mixed partial c sub hw, right? This is c sub hw, if I want to write it in a different notation, is a positive number. And remember the second partials. The second partials test, the second derivative test for extrema says, let d, right? So let d is going to equal, in general, it says the first deriv, the first second order deriv with respect to x times f sub yy minus f sub xy squared, right? Well, I'm looking here and I am looking at something. It's making me, I'm thinking to myself that if I plug in, right, the second derivative, if I plug in this value of h into this second derivative and get a value, right, and then plug in this value of w into this second derivative and get a value, and then I'm multiplying them, right? And I'm looking at f sub xy squared. This number here is just going to equal 4, right? My numerical hunch is that at the end of the day, d is going to be a positive number. That's my hunch, right? I mean, and you can actually compute these. I mean, I'm going to let you do the calculating. But this outcome tells me then, I can say, by the second derivative test for extrema, since d is positive and d squared c by dh squared is positive because h, after all, I'm treating here as x, I therefore know that a minimum cost occurs when w equals cube root of 256 centimeters and h equals 512 over 256 to the 2/3 centimeters. And of course, if I know w and h, I can find the length, right? So that is number 18, which I promised I would do out. Now, I will say this. I'm looking at my algebra. I think I may have had a little bit of a, did I make a mistake in my system? I don't think so. I think I caught it. But the calculus is super sound. I love the calculus, super sound, but I also love the fact that there really wasn't a whole lot of mess because I could use kind of like, like your spidey sense to kind of get a sense of what's going to happen with respect to the second partials test for extrema. Okay? So, Oliver, does that make sense? And everyone else, did that make sense? All right. Good night.